Swayam Prabha. Digital India. Educated India.
So, in my previous module, I have discussed about the determination of dynamic soil properties, and in this module today I will start about the liquefaction, or in this module I will discuss about the liquefaction. Now, before I discuss about the liquefaction, now one thing or the difference between the linear model and the non-linear model that I have discussed in my previous module, that I want to discuss first, and then I will discuss about the liquefaction. So, as you have already seen that the difference between the linear model and the non-linear model, both are basically representing the non-linearity of soil stress strain behavior. Okay, so under cyclic condition, but in the linear model or the actual case, your shear modulus changes every point along the loop or your stress strain curve. Now, in the equivalent linear model, so that the shear modulus is average shear modulus of that particular loop. So, that means it is a simplified form. We are representing the non-linear behavior or the stress strain behavior of the soil under cyclic condition. So, now here if I compare between the equivalent linear approach and the non-linear approach, then these are the comparisons or the differences. So, you can see that the equivalent linear approach can lead to an over softened or over damped system when the peak shear strain is much higher than the other shear strain. Suppose if you have your peak shear strain. So, in my previous lecture, I have discussed that how you can get the shear strain at every depth at which time. So, you will get the shear strain with time, shear modulus, shear stress with time, and your modulus also changes with strain. Okay, so those we have already discussed how we will get that, because in case of equivalent linear model, you have to generate the shear modulus degradation curve or damping ratio curve along with strain, and from there you will get the shear stress at shear modulus at different strain level and the damping ratio at different strain level. Then by that iteration method, you will get the shear strain, shear stress, all the values. Similarly, for the linear model also, I have discussed how you will get the shear strain, shear stress at any depth along with different time. Now, if that peak shear strain of the system is much higher than the other shear strain, then the equivalent linear approach will give you over softened or over damped system. Okay, but if your peak shear strain is uniform in nature, okay, that means previous one there is a high variation, but here it is uniform in nature, then the equivalent linear approach can lead to an under softened or under damped system when the peak shear strain amplitude is uniform. Okay. Now, the equivalent linear analysis can be more efficient than the non-linear analysis when the input motion is characterized with acceptable accuracy. If the input motion is characterized with acceptable accuracy, then equivalent linear approach is more efficient than the non-linear approach. Now, the non-linear model can be formulated in terms of effective stress. Thus, generation and dissipation of pore water pressure can be modeled during an earthquake, whereas for equivalent linear analysis, it does not have that facilities. Okay, so that is the advantage of non-linear model, that it can formulated in terms of effective stress. Thus, the generation of pore pressure can be modeled during an earthquake. Generation and dissipation both of the pore pressure can be modeled during the earthquake, but equivalent linear approach we cannot do this modeling. The parameters of the advanced nonlinear models are not as well established as those of the equivalent linear model. Because equivalent linear model, you have seen that we have to generate the shear modulus degradation curve and damping ratio curve. So those are well established parameters. Those are easy to determine or generate. But for the advanced nonlinear model, those parameters are not well established as compared to the equivalent linear model. So that is another limitation for this advanced nonlinear model, because estimation of parameters is tedious a method, or it is not well established, those parameters. Now for low strain level problems for stiff soil or weaker input motion, say, both linear approach and equivalent linear approach can produce reasonable result, but for high strain problems nonlinear approach provides reasonable results. So if it is a very high strain problem, then we have to go for nonlinear approach, because in their nonlinear approach provides reasonable results. But for low strain levels, both linear approach and equivalent, both nonlinear approach and equivalent approach can produce reasonable results. Okay, so these are the comparison between the equivalent linear approach and the nonlinear approach. Now I will start the liquefaction. So first this module I will discuss what is liquefaction, then how to know whether a soil will liquefy or not, what are the different procedures for different types of soil. So those I will discuss. Now first, the liquefaction, the definition of liquefaction is the liquefaction occurs when saturated cohesionless soil loses its strength and stiffness due to generation of excess water pressure under rapid loading in undrained condition. So now in the definition I am keeping that is a saturated cohesionless soil. Later on I will discuss when I will discuss about the liquefaction susceptibility criteria for the clays and silt or your fine grained soil. Then we will see what are the criteria to for the clay soil or the fine grained soil to be liquefied or the other phenomena. So right now I am defining it, and I will follow this definition, that is occur when saturated cohesionless soil loses its strength and stiffness due to generation of excess water pressure under rapid loading in undrained condition. So now here the rapid loading definitely is treated as the cyclic loading or that seismic earthquake loading, and because of this earthquake loading it is a rapid loading, and then it is undrained condition because the loading is very small duration, and because of that the generation of excess pore pressure, which because of that the soil loses its strength and stiffness, so that is called liquefaction. Now if under this phenomenon, that means the saturated cohesionless soil loses its strength and stiffness due to generation of excess pore pressure, if this is the case, then we can categorize that liquefaction in two groups, okay, so or in two category or in two types. One is your flow liquefaction, another is the cyclic mobility. Now flow liquefaction can occur when the shear strength of the liquefied soil is less than the shear stress required for static equilibrium, that is static shear stress. So that means the flow liquefaction occurs when the shear strength of the liquefied soil is less than the static shear stress. Okay, so that means here large deformations are produced by the flow liquefaction, and deformation produced by flow liquefaction are driven by the static shear stress only. Okay, so it is driven by the static shear stress only. So because here your shear strength is less than the static stress, shear stress. Okay, so now what will happen that because of this cyclic stress that helps to reduce this shear strength of the soil, or it reduces the shear strength of the soil, but the deformation occur in case of flow liquefaction is due to the static shear stress. Clear? That means the reduction of the strength is due to this cyclic loading, but the deformation produced by flow liquefaction are driven by the static shear stress. Clear? But in case of cyclic mobility, it occurs when the static shear stress is lower, even lower than the shear strength of the liquefied soil. But here, this case, the static shear stress is lower than the shear strength of the soil. So, but here, that's why the deformation produced by the cyclic mobility are driven by both cyclic as well as static shear stress. So, in case of flow liquefaction, cyclic stress reduces the strength of the liquefied soil, but the deformation is driven by the static shear stress. But in case of cyclic mobility, deformation produced by the cyclic mobility are driven by both static as well as the cyclic shear stress. Okay. Now, large incremental deformation is produced by cyclic mobility failure during earthquake shaking. But that means these two cases are followed by the same definition that I have given. Okay. So, now in field, flow liquefaction occurs much less frequently than the cyclic mobility, but the effects of flow liquefaction are usually more severe, but the effects of cyclic mobility can be insignificant to highly damaging. So, that means the effect of cyclic mobility can be insignificant or it can be highly damaging also, but effect of flow liquefaction is always or usually always more severe, okay, or more damaging. The flow liquefaction failures are sudden in nature, and liquefied materials often move over a large distance, because the flow liquefaction, when your shear strength is less than the static shear stress, the flow liquefaction occurs. So, that is why this failure is sudden. Okay? But in case of cyclic mobility, that this failure is not sudden. Okay. So, the deformation caused by cyclic mobility, which is called the lateral spreading, can occur on very gently sloping ground or on flat ground which is close to the water body. Now, level ground liquefaction, which is a special case of cyclic mobility, failures can occur due to the upward movement of water during dissipation of earthquake-induced excess water pressure. So, that means this level ground liquefaction, which is the special case of cyclic mobility, this failure can occur due to the upward flow of water during the dissipation of earthquake-induced water pressure. Clear? So, that means in summary, the flow liquefaction where the deformation is driven by the cyclic stress, the static shear stress, and the shear strength of the liquefied soil is less than the shear stress of the soil. But in case of flow liquefaction, the strength of the soil is greater than the static shear stress of the soil, or static shear stress of the soil is less than the strength of the liquefied soil. Okay, and in case of cyclic mobility, your deformation produced by the cyclic mobility are driven by the both cyclic as well as the static shear stress. So you can see that in case of flow liquefaction, your cyclic shear stress is greater than the shear strength of the soil. That means there is a reduction of tremendous amount of reduction of the strength of the soil due to generation of excess water pressure during the rapid loading under undrained conditions. So that's why the flow liquefaction can occur in loose sand. If I say now I am concentrating only on cohesionless soil, so I will talk about the sand. Okay, in this case, first, unless I discuss about the liquefaction susceptibility criteria for the fine grained soil, I will define this. I will only talk about the sand. So that means that's why this flow liquefaction can occur in loose sand, but as the shear strength in case of cyclic mobility is greater than the static shear stress of the soil, then this cyclic mobility can occur for both loose as well as the dense sand. Okay. So now I will first discuss about the evaluation of liquefaction resistance of soil. First, use of the laboratory test data. So first, evaluation of liquefaction resistance of soil. So how will know that the soil will liquefy or not? What are the conditions? What are the procedures? That I will discuss first. First, I will discuss the use of laboratory test data, then the field test data, and so on. So the procedure that I will discuss, those are developed by Seed and Peacock in 1971, and the Seed simplified procedure by Seed and Idris 1971. So in 1971, this procedure has been developed. So these are the two references. So you can collect these two papers, or you can read these two papers. So you will get more information from these two papers also. Now first I will discuss about that test procedure, that is discuss about the Seed and Peacock. So first we will discuss the shear stress required to cause initial liquefaction. So that means first you understand that there is a shear stress that is developed in the soil. So one thing is that how much shear stress will be required to cause liquefaction. So that I have to estimate. So for a particular soil, this is the amount of shear stress required to cause the initial liquefaction. So that first I will estimate. Another is that during the earthquake, how much shear stress will be developed. So obviously, if your developed shear stress is more than the shear stress required to cause liquefaction, then the liquefaction will occur. So that means we have to estimate two shear stresses. One is the shear stress required to cause liquefaction. Another, the stress developed during an earthquake. Okay. So first I will discuss about the shear stress required to cause the initial liquefaction. Then I will discuss how much stress will be developed during an earthquake, and then we will compare these two stresses. So obviously, if the developed shear stress is more than the required shear stress to cause the liquefaction will occur. Okay. So before we start this procedure to discuss about the shear stress required to cause initial liquefaction, let me discuss about what is initial liquefaction. Okay. So the initial liquefaction according to Seed and Lee, so this reference you will get from the Kamar 2003 book. The point at which the increase in pore water pressure or pore water pressure is equal to initial effective confining pressure So, I mean, as for the C and Lee, the point at which the increase in pore water pressure is equal to initial effective confining pressure, then that point is called, the initial liquefaction. Okay, the initiation of the liquefaction, you can say. Now, how we can rate that? So, that means, as you know that during the seismic loading, so your pore water pressure increases. Okay. The pore water pressure increases because of this seismic rapid loading and the undrained condition. So, pore water pressure increases. So, that now when this increased pore water pressure is equal to initial effective confining pressure, then that condition is called the initial liquefaction. Okay. So, I can write that if that your U excess is equal to sigma 3 bar. Sigma 3, suppose if you see a track shell, then in track shell we provide a all round confining pressure, or that is your sigma 3, similar to if your excess pore water pressure is equal to sigma 3 bar effective confining pressure. Initial means it is 0, you can say. So, sigma 3 0 you can write. So, it is confining pressure of that a point. If your U is the excess generation of excess pore water pressure is equal to the effective confining pressure sigma 3 dash, then that is called initial liquefaction, or your RU is equal to 0. What is RU? That is called pore water pressure ratio or pore pressure ratio. RU is the pore water pressure ratio. Okay. So, pore water pressure ratio RU can be defined by you can write E excess or del U is both are same. Del U is also the generation of excess pore water pressure, or U excess is the excess pore water pressure. So, RU can be defined as del U by sigma 3 dash, okay, that is for triaxial, okay, or in the field RU can be defined as del U by sigma V dash, that means vertical effective overburden pressure, that is for field. Okay, so that you can write 0 also. So, that means 0 means the initial. That means here this can be written sigma V dash or sigma V bar or sigma V 0 bar. 0 means it indicates that is initial condition, that means initial effective confining pressure. Okay, similarly you can write sigma 3 C, sigma C means under confining, okay, or consolidating. Under consolidation condition we provide the sigma 3, so that different way it can be written, right, the sigma 3 dash or sigma 3 C dash, okay. So, we will use this notation, okay. So, that means RU is here, so that means here you can write that for initial liquefaction, if your RU is equal to 0 or the excess water pressure del U is equal to sigma 3 dash, then that is called initial liquefaction. So, we are here talking about the shear stress required to cause the initial liquefaction. Okay. So, how we will do that? So, we are talking about the two test condition that we have discussed in during my previous module, the determination of dynamic soil properties, the cyclic triaxial test and cyclic simple shear test. So, we are talking about the test procedure, we will discuss about the cyclic triaxial test, that is the very common test, and the cyclic simple shear test. Okay. So, how we can use these two test procedure, and then we will get the, or you will get study the liquefaction. Okay. So, now if I go our field condition, first we will go the field condition. Field condition is what? Field condition is that this is your ground and this is a say soil element in the field which is subjected to sigma V dash or bar or sigma 0 bar initial condition, and this is subjected to a K0 sigma V dash. Okay. And it is saturated, so there will be water table also. Because the definition is mentioned that is saturated cohesionless soil. So, now in this procedure I will discuss about, I will use the term the sand. So, I am doing this thing for the sand. Right now you say this is sand, later on when I discuss about the for fine grain soil, this liquefaction susceptibility criteria for fine grain soil, then it will be clear that for which type of soil I can use this procedure and which type of soil is not. But for initial case, I will say this is for cohesionless or this is for sand or sandy soil. Clear? Okay, so that can be sand with clean sand, that can be sand with fines, but right now it is sand, or I should say it is fine grain soil, coarse grain soil. So, right now this procedure that I am discussing, it is for coarse grain soil, it can be with fines, without fines also. Okay, so that with fines, without fines, so those things we will discuss later on. But right now you say that is for coarse grain soil and for the sand, or later on I will show you during the field test that for gravel also how you can use the these techniques. So, but right now it is for coarse grain soil and for sandy soil. Clear? Later on it will be generalized. Now it is coarse grain sandy soil. So, now the field condition you can see, for the field condition this is my initial condition, that at rest condition, that means the seismic load is not applied. At rest condition, this is your soil element, these are the stresses are acting. Now, when the same soil element, when your shear stress is acting because of the ground shaking. So, this is at rest and this is during ground shaking. Okay. So, here this your sigma V dash, that will remain as it is, and this will be also K0 sigma V dash. But there will be shear stress will also develop. Okay, that is say tau h. So, this is your two conditions. One is before the application of ground shaking, that is at rest condition. Now, after when the ground shaking is applied, then there will be shear stress will develop, that is tau h. Initially only the sigma v, and that is K0 sigma v bar. So, now these are the your stress condition on a soil element. Clear? So, in the next class, I will start from this point. Okay, I will start from this point where for this is the ground condition. Now, in the field, this is the field condition or ground condition. Now, from here in the test condition, how the stresses are applied in a soil element, from there how we can correlate these two